So basically the idea is that all radiation, becomes optically thick if absorption becomes, basically if the optical depth is order unity. So let me see where I taught that. This is the emission part. So was it on December 9th? Okay, yeah, here it is. Right, so, this is the material that you want to clarify some things on.
Yes, sir.
So what is the specific point that you want me to talk about? Why does absorption happen, right? So this is just an application of Kirchhoff's law. So we derived the emission properties of free emission, that is, we got J nu, right? And since it's a thermal emission mechanism means that the particles which emit have a Maxwell-Boltzmann distribution, and the collisions between particles are enough to set up a Maxwell-Boltzmann. So in that case, your S nu, the source function, is B nu. So this alpha nu is just J nu by B nu, and we know the emissivity of this plasma. We did all this, we derived it in the class. So we get this for alpha nu FF. Right? So this is absorption coefficient in per centimeter for a plasma with number density Ne, Ni, charge state Z. So what is it that you want me to explain a little more?
I didn't understand why the plasma becomes optically thick at the low frequencies. I mean, why is there a breaking frequency, new break?
Right. So at low frequency, this alpha nu becomes larger and larger, right? So if you look at the nu dependence of this alpha nu, it goes like nu to the -3, right? So T is the plasma temperature. So for everything else fixed, right, this alpha nu goes like nu to the -3. Is this clear?
Yes, sir. Yeah.
And in the Rayleigh low frequency regimes, h nu less than kt. In fact, this goes like nu to the -2. This is nothing but this behavior of B nu, right? This nu to the -3 really comes from this B nu, because J nu is more or less independent of nu for Bremsstrahlung emission. It's only at the break frequency that you have this exponential cutoff. So what happens is at low enough frequency, your alpha nu times length becomes order unity. That is, your medium becomes optically thick. Okay, and when it becomes optically thick, so it will become optically thick at all frequencies below this break frequency. Okay, so this is what determines that break frequency. Right? So if you have some column, then some volume of this plasma, then you just say, when is my optical depth order unity? Tau nu. In fact, it really should be tau nu. So you say that. So this is tau nu. So this is the frequency at which your medium will become optically thick, and this is what the expression was, right? That if the density is high, nu break is high, so it becomes optically thick at higher densities. If temperature is low, it becomes more opaque, and that also again comes from this dependence here. Okay. Is there anything else, Vishnu, that you want me to?
Yeah.
You know,
Okay, so I got it now.
see, the point is,
No need.
this is really the point, right? Whenever alpha nu times L becomes order unity or greater than that, a photon which is generated here will not just free stream like this, right? It will not just leave like this. It will undergo random walk, and that's when you start establishing a black body spectrum. So it has to become black body on this part, right? So this actually is applicable for any mechanism, right? This is just the definition of when does a medium become optically thick, right? So here we are using a specific form of alpha nu, which is valid for free emission, and we get this. Is it clear?
Yes, sir. Got it now.
Okay, good. Okay, so some people did not appear for the second exam. So I mean, if people are still thinking of dropping this course, 15th December, which is tomorrow, is the date for dropping this course. Okay, so this is the dropping date for this course not to appear in your transcripts. This option is only available for people for whom this course is not a compulsory course. So it doesn't apply for JAP people. JAP people have to take this course. But others who are, for whom this is an elective, can drop this course if they wish by tomorrow, and the course will not appear in your transcripts. Okay, because I saw some people did not appear for the second exam. And if you decide so, please let me know on chat or on email. Okay. So any other question?
No, sir.
Okay, so last time we started synchrotron emission. So again, the plan is actually to go through these different astrophysically relevant processes. So we finished Bremsstrahlung. Now we are in synchrotron. So in synchrotron emission, you have these magnetic fields, and you have electrons going around magnetic fields in helical motion. So in this case, acceleration is towards the magnetic field. So and acceleration is perpendicular to the velocity. So we did these two special cases when acceleration is along the velocity and when it is perpendicular to the velocity. So this is that cartoon case when acceleration is perpendicular to the velocity. So in the particle rest frame, this is your dipole radiation pattern. And now if your velocity is perpendicular to acceleration, this lobe gets forward beamed and this sort of gets suppressed. And the forward beam is of order 1 by gamma, angle is of order 1 by gamma. So this is really the fundamental reason that synchrotron emission is very different from cyclotron emission. Cyclotron emission basically refers to emission from this rotational electron motion when the velocity of the particle is much less than c. Right? In that case, what you see is you see one dipole oscillating like this, another oscillating like this, and they have a phase difference of pi by 2. So what you have is a linear combination of dipole radiation in this direction and in this direction if you're looking into the plane. If you're looking here, you only see this direction, because if you have acceleration along the line of sight for non-relativistic particles, you see 0. So this is sort of like the exam problem with electric field that I asked. But this is cyclotron emission. This also happens in some cases. For example, in planetary magnetospheres, in sort of neutron stars, sometimes you see cyclotron emission. But the most prevalent example of magnetized plasmas radiating is when the velocity of these particles is relativistic. So when the electrons are moving close to the speed of light, then the nature of the cyclotron emission changes fundamentally because of these relativistic effects, and that emission is called synchrotron emission. So last time we derived this, this cyclotron motion of particles around magnetic fields, and these particles gyrate around field lines at this frequency, this which is called the gyro frequency, which is QB by gamma MC. This gamma M is just the mass becomes heavier when it moves, right? Because M goes to gamma M, right? So this is that effect that if the particle is moving, its mass becomes gamma M. So this is this gyro frequency. This is the frequency at which the particle is rotating around magnetic fields. So the particle motion is in form of this helix, and this, so right, so this is the right, so so the velocity sort of lies in a cylinder. So let me see if I can draw it nicely. It's important, this is very, very fundamental, you have to like know this extremely well. So let's see. So, in general, the particle is doing this helical motion, and at every point, so the velocity at every point here, it's sort of, this velocity lies in a cylinder, and at every point, this velocity makes an angle alpha with respect to the direction of magnetic field, which is taken here to be the z-axis. So this is called the pitch angle, right? And this is the, so this is the perpendicular velocity, v perp, and this is parallel velocity along the direction of magnetic field. So and the acceleration is in this direction, right? Acceleration is in the minus r hat direction. So if we use cylindrical coordinates are a good choice in this case, because right, because you have magnetic fields which imposes a cylindrical symmetry. So this is minus r hat. The acceleration is in the minus r hat direction, and the velocity, so velocity does not have any radial component, it's sort of doing circles, but velocity sort of, if I draw this cylinder, right, so this is sort of like in velocity space, and your velocity is sort of going around like this, and around this cylinder. So this is v perp, and this is v parallel, and this is actually the velocity, and this is the pitch angle alpha again. Okay, so acceleration, so velocity vector lies in the z theta hat plane, right? It sort of lies along the surface of these cylinders. Acceleration is perpendicular to the direction of velocity. So acceleration is along minus r hat. So this r hat is like the cylindrical coordinate that I'm choosing. Velocity is in, so there is zero radial component, and it has v r phi z, so v phi v z. V phi is sort of like a v perp. Okay, good. So that's why a perp, so a parallel is 0 in this case, right? Because velocity lies in the phi z plane, and a is in r hat. So a parallel is 0, and that's why you apply this formula with a perp. Acceleration is perpendicular to velocity. And this is called Larmor radius. So when we actually, so this is the perpendicular equation of motion. Parallel equation of motion just says that the velocity along the field lines is constant, and this is the perpendicular velocity of motion. So from circular motion we know that dv perp dt is the centripetal acceleration, which is just this v perp square by radius of this circle, and this right hand side is the force. Right, so I've actually just taken the magnitude. So so this is v perp squared by r equals the force divided by mass, which is qv perp v by gamma. So this is the Larmor radius. This is the radius of this circle in the perpendicular direction. So basically this radius is the Larmor radius in the perpendicular plane. In the plane perpendicular to the magnetic field lines, the circles that it sort of undergoes has a radius equal to this. This is just a consequence of circular motion and centripetal acceleration balancing the centripetal Lorentz force. Right, and also remember that if the magnetic field comes out of the board, right? If magnetic field comes out of the board, so this is an electron, right? Because phi hat cross z hat is phi z is r hat. So electron better be negatively charged so that the force points towards the center, and the proton will be in the opposite direction. So we only consider electrons because they are lower mass and they accelerate much more than massive protons. Okay, so let's get started with today's class. So right, so we will actually, so just a few things. It's a good idea to actually memorize certain things, which I'll sort of mention, just so that you can quickly sort of get a feel for the regime in which you are in for synchrotron emission. Just a sec. Okay, let's get started. So we'll actually do qualitative treatment. Of synchrotron radiation. Okay, so as opposed to cyclotron radiation, in synchrotron radiation, particles are moving relativistically, and of course acceleration and velocity are perpendicular to each other. So so if the acceleration is in this direction, and in the particle rest frame, if this is your radiation beam, and if you are moving, if this is the velocity of the particle in lab frame, so this is in S prime, in frame S it becomes beamed in the forward direction, with this angle being of order 1 by gamma. So most of the radiation, most of the electric field is actually confined to this narrow beam along the direction of velocity. So this is the direction of velocity. This is beaming and aberration effect. So let's actually consider. Let's consider this particle going around in this helical motion. Okay, so let me actually draw this part of this helical trajectory. Okay, so from last time, that not last time, just before I mentioned that a particle is undergoing this helical motion. Right, so this is that angle alpha, this pitch angle. So what I'm drawing here is this. So this is the plane which is going in this direction. Right? So this is the plane of motion. This is the direction. This is the direction of velocity. So I actually cut it, and since this particle is actually moving close to the speed of light, so this, so you know, this thing that I've drawn here is basically along that, along v hat, right? So this is the velocity. It has a component along the magnetic field and a component perpendicular to the magnetic field. So this is a, you know, this is like an orbit of this particle for a short time along this helical trajectory. Okay, so what happens is, right, so this is the velocity of this particle, you know, along this direction, and what happens is that right, so I mean, here it's sort of like a, locally you can sort of think of it as a circular motion, right? And so this is the velocity here. This is the velocity here, and what we are saying is that the radiation is actually beamed. So you know, if you have an observer in the horizontal direction watching it, so let's see, let's connect this line. Okay, so and you know, we consider this beam. Consider this beam. See, this is a beam of half angle 1 by gamma. Right. Again, particle velocity is the same. It's constant. Absolute value of v is constant. Sorry. So this is the direction of this velocity. So the beam would be just a sec. So this is sort of the beam of the radiation. As I said, radiation is only mostly focused in a narrow beam, like a lighthouse beam, right? So you know, when there is an observer, the observer only sees the particle only during from this point 1 to point 2, right? Because in this part of the so you know, this is some arbitrary observer. So let's see. I mean, this is the observer basically. I mean, he's actually looking along the direction of velocity, but since because of this forward beaming, you know, here, you know, the direction of velocity is, you know, the velocity is beamed in this direction, right? So this observer will not be able to see any electric field from this location. Is it clear? He or she only sees the light, appreciable light, when the particle is between positions 1 and 2. Okay. So let's call this angle delta theta. Okay, and this sort of is angle 1 by gamma. Again, this angle is 1 by gamma, and this just comes from this idea. Okay. Now this right. So if the observer, you know, this is not an arbitrary observer. This observer is at an angle, right? This observer is at an angle alpha from the vertical, right? So this is actually, this is an observer for whom velocity is along line of sight. Right? So if you had an observer who is watching from here, you know, for these guys, velocity is never along the line of sight, right? Velocity is always at an angle, so he will not see as strong a radiation. Do you get this? If an observer is in this direction, beams are only in this direction, right? About the velocity. Only for a small path do you see this beamed radiation, which is shown here. So this, we are actually considering an observer for whom the velocity is along the line of sight. Okay. Let's see. And this is only like a part of this full Larmor orbit. So, the radiation is only seen for a small portion of the circular orbit between this point 1 and 2. Okay, so let us call this length, this arc length between 1 and 2, this arc length. Locally we can approximate it as a circle. Any curve we can locally approximate by a radius of curvature, and this A is this radius of curvature of this circle. This is not the same as the Larmor orbit, because right, it is sort of it has some angle alpha which is not pi by 2. So this is A, this is the radius of curvature. And this delta S is the arc length from point 1 to point 2. Okay, right, by definition, delta S is equal to A delta theta, right? So this is radius of curvature. Radius of curvature times the angle is the arc length, right? This is the definition of radius of curvature. And yeah, since this angle is so since this angle is delta theta, right? So this angle is 1 by gamma. This is pi by 2 minus 1 by gamma. And this is 1 by gamma, right? This is 90 degrees. So delta theta is equal to 2 by gamma, right? Because it's a simple geometry. This is 1 by gamma. This is also 1 by gamma. This is symmetric. Okay. So delta S equals A times 2 by gamma. Okay, and we know, but just a sec. Twice A by gamma, and we also know that this is equal to, this is the length of the arc, is equal to V times delta T, where delta T is the time that it takes to go from point 1 to point 2. Okay, we also know that the equation of motion is gamma m d v dt equals q by c v cross b. So, or gamma m delta v by delta t and we know that right, so delta v is equal to v delta theta, right? So this is like, if this is like a part of a circle, and in fact let me just write the magnitude here. And if this is part of the circle and this is delta theta, the change in velocity from 2 to 1 is just this, and it points towards the center of this local circle. So if we just take the magnitude of this equation, so this just becomes magnitude, just a sec. And V and B are perpendicular. No, A and B are perpendicular, but V and B have an angle alpha between them, right? So this is Q by C, VB sine alpha, right? V cross B, magnitude of that is VB sine alpha. So this is just that. And so gamma, so the gamma M delta V is just gamma M V delta theta by delta T is equal to Q by C VB sine alpha. So, but we know that, right, so delta T is delta S divided by V. So we can actually write it as is delta theta by delta T is equal to 2 by gamma. 1 by delta T is V by delta S. So gamma MV is equal to Q by C VB sine alpha. But I want to write it in a special form. So 2 by let me retain it as delta theta. So V and V. So basically delta theta by delta S is equal to, basically this is delta theta and this distance is delta S, is equal to QB sine alpha by gamma M V times C, right? So delta S by delta theta is nothing but, delta theta by delta S is nothing but 1 by A, right? So or A is equal to right, so this thing EB A gamma M C, this is nothing but omega B. This is equal to V so A goes there, so V by omega B sine alpha. Okay, so this is your radius of curvature in terms of velocity and the gyro frequency. Now, if you recall, your Larmor radius was V perp by omega B, which is equal to V sine alpha by omega B, right? So therefore A is equal to RL by sine square alpha, right? So the local radius of curvature is larger than the Larmor radius by 1 by sine square alpha. This is the local radius of curvature. And Larmor radius, you recall, was this radius of this circle, seen from the top for the circular motion around magnetic fields. Okay, good. So as you can actually see that when alpha, so alpha is equal to 0 corresponds to the zipping motion along the magnetic field direction. There is no circular motion, right? In that case, the radius of curvature is actually infinity, right? Delta S is equal to twice A by gamma, which is equal to, so now we know this A, so we can actually substitute. This is 2V by gamma omega B sine alpha. This is just A delta theta. So this is your delta S. So this is a short distance, and this is also equal to V times T2 minus T1, right? So T2 is the time when the particle is at position 2, and T1 is the time when the particle is position 1. Now these are the times when the particle is here. What about the times when this pulse of radiation, which is really, the photons which are released at 1 are captured by the observer at time, say, T3, right? So T3 and T4. This is again, so what I'm actually trying to do is I'm trying to write this time difference between 1 and 2 in terms of the time when these signals are measured by the observer. So we know this is sort of the light chasing light effect, right? Because the particle is moving close to the speed of light and light is emitted. So the particle actually travels quite a lot as light moves towards the observer. So let T1A and T2A, actually not T3, T4, let's call it, just to be consistent with the notation, let's call it T1A. So the arrival time of the photons emitted at time T1, and T2A is the arrival time of the photons emitted at the position 2. So how do we calculate it? It's simple. We actually did similar thing previously. So in fact, this is along the side, so it's even simpler. So T1A is equal to T1 plus delta S by C plus D by C. Suppose this observer is at a distance D. So this arrival time of the pulse which leaves the source at T1 is nothing but C times T1A minus T1 is equal to this total distance D plus delta S, right? Whereas T2 arrival time is equal to T2 plus D by C, right? I mean, this has an extra time to travel, so T2 minus T1 arrival time is equal to T2 minus T1 minus delta S by C, right? But we know that delta S by C is equal to this guy, right? Is equal to V by C, T2 minus T1. So V by C, T2 minus T1. So this is equal to 1 minus V by C, T2 minus T1. So the arrival times when V is close to C can actually be much shorter than the emission times. So this is exactly the light chasing light effect. I mean, this has come up so many times, this 1 minus V by C factor. And you can actually easily see this, that if this particle at 1 is traveling at C, then all the photons which are emitted from point 1 to point 2, all of them will reach the observer at the same time. So delta T will be 0 in that case when V is C. Okay, so this is another thing that because in the end we want to characterize the radiation as seen by the observer, right? When we are sort of characterizing synchrotron emission, we want to characterize how the observer sees it. Okay, so what is this? This is equal to 1 minus V by C is nothing but when V is tending to C, this is equal to 1 by twice gamma squared, right? This factor. Everyone knows this? 1 minus beta. So gamma squared equals 1 minus beta squared inverse, right? And beta is close to 1, so this is approx. So this implies this is actually 1 minus beta squared is equal to 1 by gamma squared. So 1 minus, beta is equal to 1 minus 1 by gamma squared half. Gamma, so when beta is close to 1, gamma is close to, is much bigger than 1. So this is approximately 1 minus 1 by twice gamma squared. So 1 minus beta, which is 1 minus B by C, is 1 by twice gamma squared. This is very important to know. That's what I'm using here. 1 minus beta is 1 by twice gamma squared. So delta T arrival, which is nothing but this, is equal to 1 by twice gamma squared T2 minus T1. And we know that T2 minus T1 is nothing but 2 by gamma. So from this, we can relate T2 minus T1 to 2 by gamma omega B sine alpha. So is equal to gamma cube omega B sine alpha inverse. This is actually very, very useful. So the arrival time, right, it can be much shorter than your 2 pi by omega B, which is just the Larmor period, right? So the cyclotron period is 2 pi by omega B, is much bigger than delta T arrival, right, for relativistic particles. So now what does it mean? What it means is that when a particle actually undergoes this motion and someone is looking from this direction, you only see this particle at this location, and these paths you will not see it. Again, you see it at this location when it comes back here, and so on, right? Whenever the particle is moving towards you, you will see it for a short time, and that time is this delta TA given by this. So the electric field measured by observer sort of looks like this. It sort of looks like this. So, you know, you have this pulse of you have this pulse of duration delta TA, right? So this is again delta TA, and these are separated by, right, the Larmor, this time period, the circular time period, which is 2 pi by omega b. Right, the separation between them is basically given by when does this particle complete a full orbit. But this time, delta TA is gamma cube, sort of gamma to the -3 times, let me not write it. Let me just sort of leave it at gamma. Oops. Undo. Oh. Why does it delete the whole thing? Okay, let me just write. So this is much less than 2 pi by omega b. Let me just write this. Okay, so is this very clear? This is really the fundamental physical process that's happening. Okay, later on we'll go to mathematical description of this, but this picture has to be very clear to everyone, that you have this particle undergoing these helical motion, and even when you're sort of looking at the line of sight, only for a specific duration do you see the emission from this particle. Only when this 1 by gamma beam is along the is along the line joining the particle and the observer, along the line of sight, basically. Is this clear? Yes. Hello.
Yes, sir.
Okay. And this is also clear. Why do you see such pulses? Right. This is the full Larmor orbit, and this is only for the time when, the beam, this lighthouse light is directed towards you, only for a very short time. Okay. So now if you think, so this is like your electric field. This is sort of like a electric field, or the magnitude of the electric field as a function of time. Now we have learned a little bit about the Fourier transforms. So you'll see the maximum frequency of this time signal occurs at, right? So let me actually do E omega square. Just sort of qualitatively, let me draw it as a function of omega. How would that look like? So, your maximum value of omega occurs at omega b in at this delta TA inverse. So, so omega cyclotron, twice omega cyclotron, and so on. So this omega cyclotron is nothing but sorry, not omega c, omega b. Let me write it as omega b. Right. So this, you will see these peaks, these Fourier peaks, at the harmonics of the cyclotron motion. Okay, but you will see it will be a very broadband spectrum. So you will see energy cutting off exponentially at a frequency which is corresponding to this time scale. This is, let's call this omega c, and you have power at all the harmonics of omega b, and this omega c is equal to, let me just sort of write it down, so 3/2 gamma cube omega b sine alpha. So I have introduced this 3/2 just so that it matches the exact results or exact conventions. So basically there is a continuum. So this is a continuum spectrum. So there is a continuum of there is power at all these omega b, 2 omega b, 3 omega b, and all the way up to gamma cube omega b sine alpha. This gamma cube can be really, really big. So if gamma is 100, so this can be 10 to the 6 times omega b. So you'll have 10 to the 6 harmonics, right? If it was a non-relativistic motion or mildly relativistic motion, you only see these, right? Now you've gone to a power which is 10 to the 6 times higher frequency photons compared to the Larmor frequency of the Larmor motion. So this is omega c, and you can actually nu c is equal to omega c by 2 pi. So you can also talk in terms of the frequency rather than the angular frequency. Okay. Okay. So let's see, nature of electric field that's sort of measured by the observer. Right. So when gamma is much bigger than 1, right, we derived these dp radiation d omega, right? We derived these expressions and they were only a function of gamma theta. If you recall, right, that for very fast particles, the power that's observed or the electric field is only a function of gamma theta. Or in other words, right, we said that there is this forward beaming of radiation over an angle of 1 by gamma. This is the direction of velocity. Now the electric field profile as a function of this angle theta, this general angle theta, right, only depends on, right, so that if we write electric field as a function of angle theta, what we are saying is it depends on theta only through this gamma theta factor. So when electric field is maximum on the axis and it decays. So something like this, it's symmetric in minus theta plus theta, and it sort of cuts off when gamma theta is order unity, right? So electric field is a function of only gamma theta, right? So this profile, whether you do for gamma equals 100, gamma equals 1000, right, you can scale it to each other. Right, if you're doing it for gamma equals 1000, you just make it narrower by a factor of 10 compared to gamma equals to 100. So electric field is only a function of gamma theta. We actually showed it mathematically too when we are doing dealing with this power radiated power formula. And so, you know, basically this is we can actually just say this. So let's see, electric field observed as a function of time, right, is equal to some function of gamma theta. So, you know, this is the observer direction. So as the particle is sweeping towards the line of sight, right, this is, you know, this position is sort of like a 1 position, this is sort of like a 2 position. So, and this is like when the particle is along, moving exactly along line of sight, right? So theta equal to 0 corresponds to this position where particle is exactly along the line of sight. Okay. So let's actually look again back at that curved motion, and let's call this. So this is theta equal to 0. So so we know that theta is equal to S by A. This is just the definition. So S is starting now from being measured from here. So this is the length S, the arc length. So theta is equal to S by A, and time, you know, is equal to S by V times 1 minus V by C. Right? So this is the arrival time, right? This is the time measured by observer. So this is really a T arrival. So this S by V is just the time, you know, S equals Vt, but this extra 1 minus V by C comes from the light chasing light effect. Okay, so using these two, we can actually relate time and theta. There is a 1-to-1 mapping between theta and time, right? So when theta equal to 0, we take time equal to 0. So we just divide, you know, we just eliminate S out of this. To these two relations, what we get is right, and this is equal to S by V. 1 minus V by C is 1 by twice gamma squared. So if we take the ratio, so theta by T is equal to 1 by A. So theta by T is equal to S gets cancelled, so there's 1 by A twice gamma squared. V is nothing but C. Okay, so, and we know from above we can actually substitute for A here, no? This is your A. So A is V by omega B sine alpha. We just erase A. So gamma theta is equal to twice gamma cube. So as I said, the electric field is only a function of gamma theta. So I'm actually writing gamma theta as twice gamma cube. So, you know, this B and C get cancelled. Omega B sine alpha times T. So this is the relationship between theta and T. So T equal to 0 corresponds to theta equal to 0. that corresponds to the maximum of the electric field, sine alpha t. And this is nothing but, this is proportional to this omega ct. This is the cutoff frequency. This omega c is cutoff frequency for synchrotron emission. You can actually see, right? This is, the gamma cubed omega b sine alpha. So this is just omega ct. Okay, so let's see. Let me actually mark a line. So the electric field, right, measured at the particle's position, actually the magnitude of this is proportional to it's a function of gamma theta, and gamma theta is nothing but omega c times. So this is proportional to this, just some function g of omega ct, right? Because gamma theta, right, gamma theta is just omega c times time. So this is, I'm just sort of saying, again stating the fact that electric field magnitude is a function of gamma theta, which is expressed in terms of time t now. Okay, now E is equal to, right, so let's this is like the electric field, the Fourier transform of electric field, right? This is proportional to minus infinity to infinity g omega ct e to the I omega t dt. Right, so we want to do a change of variable. Let's define xi is equal to, so change of variables. So let's define xi equals omega c times t. So if we do that, so this thing becomes proportional to minus infinity to infinity g c e to the I omega by omega c and dt is 1 by omega c dc, right? So so this is also, this will be, so the frequency dependence of this thing will be some function of omega by omega c, right? Because you're just integrating a function of omega by omega c. So this will be some function of omega by omega c. So basically the power spectrum, the frequency power spectrum of electric field depends on frequency only through omega by omega c. Okay. So wherever you have frequency dependence, it appears as omega by omega c. That's the idea. And this omega c is just this. Where is this one? So wherever in the synchrotron processes, wherever you have frequency dependence, it appears as a function of omega by omega c. And omega c is given by this. Okay, so spectrum. So the power, this is the spectrum, is proportional to E omega whole square. And so what about angle averaged power per unit frequency? Whenever we have radiation, we deal with the spectrum, the frequency response. We deal with angular, angular distribution of power and so on. So we are again doing the same thing. What is this? This is dW by dt t omega. This is nothing but 1 by t. Now this time period is nothing but 2 pi by omega b. Because this is sort of like, you see a pulse every time t, period capital T, times d omega by d omega. So this is your angle averaged power per frequency. Let's call it power, the function of frequency, and this will be equal to some constant times a function of omega by omega c, right? Because this is a function of omega by omega c, and this is nothing but e tilde omega the whole square. So this will also be some function of omega by omega c, and c1 is some dimensional. This is some dimensional constant. Okay, so but we know that we know the total synchrotron power, right? P synchrotron omega is equal to not omega. So we know this total synchrotron power. This is equal to integral P omega d omega 0 to infinity, right? We know the total synchrotron power. So this would, right? So this is just the angular integration. Right, we had actually calculated this from Larmor formula. So we are trying to determine this normalization. This is equal to C1 times F omega by omega C times d omega. So let's just do this. Now this is nothing but omega C C1 integral fx dx. I know this is just a number. This is just a number, like 1, 5, whatever. This is just a number. And what was this? P sync, we had derived it from the Larmor formula. This is equal to, then we write it down. So 2q4 b squared gamma squared beta squared sine square alpha by 3 m square cq. Now this is just obtained from the Larmor formula. This a perp square gamma to the 4 a perp squared formula, right? And we had actually written in the last class. So this is, again, the important thing is to realize this beta square, b square gamma squared beta squared dependence and sine square alpha. Okay, so, and we know that omega c is that. Let me just write down omega c is equal to, what is omega c? It's 3 gamma square qb sine alpha divided by twice mc. So this is my omega c, this is my total power. So so my C1 is nothing but it's proportional to the ratio of this and this, right? So C1 is proportional to the ratio of my synchrotron power and omega c. This is just a number, so that's proportional to. So let's divide this by this. What do we get? We get, and we can take beta 1. So what do we get? So this gamma square cancels, there's a b, so this is proportional to b sine alpha. And other fundamental constants. So in the end, what we can actually do is we can write p omega, the power, as a function of frequency, right? So this was frequency averaged, frequency integrated. Here is how it will be. Let me just write down. So you know, these constants that I write down in front are motivated from the exact formula that we'll talk about later. So this is cube b sine alpha divided by mc squared f omega by omega c. So so this is what our power as a function of frequency comes out to be. Right, so the dimensional dependencies are there, you know, it's just this ratio. So your C1 is proportional to b sine alpha, that's what you get. This gamma square cancel when you take this ratio. And it better do, because we said that the final expression that we have will only be a function of, it will have frequency dependence only through omega by omega c. Okay, so this square root of 3 by 2 pi, they are just put in because by anticipating the answers that we get. The more important thing is this dependencies, right? Q4 divided by Q is Q cube. There's a proportionality to B and so on. Okay, so this is your power formula. And you know, this is motivated by the more exact results that we'll talk about later. Okay, so right, so we had this, right? So oops. Oh, I created it twice. So let me just delete this. I created these. Delete. Okay, so I hope I haven't deleted the class. Okay, no. Right, so the key thing here was right, so the power, the synchrotron power as a function of frequency only depends on frequency through this combination omega by omega c, and omega c is this proportional to gamma cube omega b. This is very, very important. Okay, and this is just this is independent of omega. So as claimed, my electric field is only a function of gamma theta. And my frequency dependence is only omega by omega c. So this is power p omega, but we know that we can also write it in terms of p nu. So p nu d nu equals p omega d omega. This is just the definition of power. So the power from nu to nu plus d nu is equal to power from omega to omega plus d omega. So p nu equals p omega times d omega by d nu. This is equal to p omega nu is by 2 pi. No, p omega times 2. So I'm always confused. So nu is equal to 2 pi in omega. So d omega okay. So just a sec, e to the minus I omega t, or e to the minus 2 pi I nu t. So omega equals 2 pi nu, sorry. Okay, so 2 pi nu equals omega, so this is equal to d omega d nu is 2 pi. So, you know, it's very easy to go from omega to nu. Just know this. Okay, let's go to okay, so what did we do till now? We dealt with a single electron, radiation from a single electron, and we looked at this particular line of sight in which the electron, you know, is pointing exactly towards the line of sight along its motion. Okay, now what about a power law distribution of electrons? And you know, we also dealt with a fixed pitch angle alpha, right? We had a particular choice of alpha, so we will actually have to deal with like a distribution in alpha. So let's first start with the power law distribution of electrons. So let's see. Right, so now this is the right. So you have this you have these relativistic electrons, and they have a power law distribution. So let me define what I mean by it. So I have n gamma d gamma equals c times just a sec, times gamma to the minus p d gamma, right? Or we can also sort of, you know, E, energy of this relativistic electron is equal to gamma me c squared. So, you know, there is a 1-to-1 relation between gamma and E. So sometimes people also use E instead of gamma. So you have like relativistic electrons which have like say n gamma as a function of gamma. If it's a log-log plot, you have like a power law distribution, right, with gamma to the minus p. So it has a slope of minus p, and it has some, you know, range of gamma min to gamma max, right? So this is the power law distribution of electrons. If you have such electrons, the question is, how does my so the question is, how does the synchrotron power vary as a function of omega? This is the question. Right, so basically p omega is proportional to omega to the minus s, right? And this s is sometimes called s is equal to -2, for example, for Rayleigh-Jeans slope of black body. So So this is called spectral index of, say, radio emission, spectral index. So we want to get the spectral index in terms of this distribution, the power law distribution P of these electrons. Okay. So from the previous slide, from the previous part, we learned that power from a single electron. So how do we do? How do we get the power per unit volume per unit frequency is equal to, right? So basically this is what we do. N gamma d gamma times power. So this is power due to single electron, and this is the total number of electrons. This is number of electrons per unit volume. So this power due to single electron per unit frequency. So this is number of relativistic electrons per unit volume with their gamma in this range. Okay. So this is this, right? So all you have to do is you have to sum over all these electrons. You have to sum over all these electrons. We know for a particular gamma how much power comes out from the power formula. You just have to add these up, contribution of all these electrons. Okay, so how do we do? So P total as a function of omega is equal to, okay, so this is just C, so integral C, this is that normalization constant C, gamma min to gamma max, P omega gamma to the minus P d gamma. Okay. And if you recall this expression for a single electron, P omega for a single electron is proportional to B square times a function of omega by omega c, right? Some function of omega. Well, let's actually go back to the previous part. Come on. By the way, any question? Okay, we are there. So you see this expression, this is P omega. This is power due to a single electron, and it's proportional to it's proportional to this Q cube B and this F omega by omega C. So let's go back to let's get rid of this. This was actually not B square. This was B. Okay, so how do we do? Right, so we know that so this is equal to constant times gamma min to gamma max. This is B times a function of omega by omega c, and gamma to the minus P d gamma. Okay. So let's do a change of variable. X equals omega by omega c, and you recall that this is equal to omega by, I mean, it's proportional to, there was EB by gamma MC times gamma cube, right? So this was the proportionality. So this is equal to omega MC by EB gamma squared. So the frequency by omega c is just related to this. So dx. So there is a one-to-one relation between x and omega. All right. So this is a change of variable from omega to x. Sorry, just a sec. Right, so frequency is fixed, frequency is out of the integral. So there is a one-to-one relationship between x and gamma actually. Frequency and B are fixed. So gamma is proportional to omega MC by EB to the 1/2 times x to the minus 1/2, right? I mean, this is just this x equals omega MC by EB gamma squared. So gamma, and there's a proportionality. So d gamma is proportional to, let's just retain omega B and x. So omega by B half x to the minus half. So it becomes x to the minus 3/2 dx, right? I'm just sort of taking the derivative. There's a negative sign. Okay, so this is fine. So now, right, so now we can actually see that this is proportional to omega by, right, so this is some x min to x max. Gamma and x have a one-to-one mapping, and there is a B here, and this f, there is f omega by omega c is x, fx. Gamma to the minus p is just omega by b minus p by 2 x to p by 2, right? I'm just sort of substituting for this gamma to the minus p from here, and I'm just retaining omega and b dependence. And d gamma is omega by b to the half x minus 3/2 dx. Okay, so now this x integral will be just a number, right? Because x is dimensionless. So what do we have? What we have is, right, let's look at the omega dependence, right? It's proportional to omega to the minus p minus 1/2, right? You see, this is omega to the minus p by 2 and 1 plus 1/2. So this is omega to the minus p minus 1/2, and we have b. What is the power of b that we have? There is a plus 1 here, so plus a half. This is plus a half minus p by 2. So this is p plus 1/2. Right, and then there is just a number times a number times some constant. That number is just this x integral. So we have retained the frequency and magnetic field dependence of this power due to this power law distribution of electrons. So we have this power law of distribution of electrons. We had derived this dependence on omega. We had derived this dependence on omega for a single electron. Now we have to sum over a population of electrons, and there is a one-to-one relationship between this gamma and omega by omega c, which we just call x, right? So we have this, and what is the spectral index now? Spectral index is equal to p minus 1 by 2. Right, and this was my spectral index, the definition of spectral index. So I can just read off what S is. S is just p minus 1 by 2. So so we actually, this is a very useful result. This is actually very frequently used. So if you have a power law distribution of electrons, how does the synchrotron spectrum go as a function of frequency? This is, and as a function of magnetic fields. So this is what you get. Let's see. So let me actually show you some examples. There are some synchrotron emission examples from real astrophysical objects. Okay, so what I'll actually do is, since I cannot annotate here, I can take a snapshot and put it in there. Let's actually, let me just, yeah. Okay. 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 So I will always show you examples, because otherwise these can just become very tedious formulae without much insight. Hopefully this is, yeah, so here it is inserted. I want to expand it a little bit. How do I want to make it a little bigger. Just give me a, okay, good. Make it bigger. Awesome. Okay, so this power law distribution of electrons is very common in astrophysics. You almost always invoke this power law distribution. So let's see. So this is a well-known radio source, Crab Nebula. Okay. Now here, so this is the observed spectrum of Crab Nebula. In fact, this is a nebula powered by the wind of this pulsar, Crab pulsar. So here, this is what our optically thin synchrotron emission. In fact, in this case, the synchrotron emission comes not in radio. The radio part is self-absorbed. It comes in, you see 10 to the 18, you see the energy here is 10 to the 4 eV, 10 keV. So this is optically thin synchrotron emission in X-rays, which is very rare. It comes out in X-rays because this is very, very magnetized object and very relativistic particles, So two things to remember are that, just these scalings, right? One is nu observed, the frequency of the observed synchrotron emission is equal to, is roughly scales as gamma square, or gamma cube nu omega b, but we sometimes call it gamma squared omega cyclotron, and omega, so right, omega b was nothing but EB by gamma MC, right? Sometimes we define omega cyclotron as EB by MC. If you do that, this is just omega gamma square times omega cyclotron. Now, if you see this radiation, right, and this is optically thin, so if the magnetic field of the pulsar is, say, you know, wherever this is coming from, say, is, you know, whatever, 10 to the 6 Gauss, right, then you can actually get the gamma of electrons which cause the frequency at 10 to the 18 hertz, right? So, you know, 10 to the 18 hertz is equal to your nu, this observed frequency, and you know EB by MC, which is equal to your omega cyclotron. So we can actually just get gamma for the gamma of the electrons which are responsible for these points is just omega by omega cyclotron to the 1/2. Right? So we can actually calculate it. And, you know, it turns out gamma of 1000, 10 to the 6. So, you know, these are very, very relativistic, right? So, and this is optically thick in radio part, right? This, where is radio? This is radio. 10 to the 9 is 1 gigahertz, 10 gigahertz. This is sort of radio. This is, oops. Where the, oh, just a second. So this is from a radio galaxy. This is from a galaxy. I don't know what is that. Right, so this is from a galaxy. So here, this is optically thin. Now this is at this you know, now this is like this is your this is like nu to the minus p minus 1 by 2, right? This is your power. So this is flux, which also is must. So this is a log plot. So you can actually measure the slope from here, right? The slope measured here is the spectral index. Once you know the slope here, you know what your P is, right? This is an observation. So from observations, you can get what is the power law distribution of your electrons. This is very, very powerful, this formula that we derived today. These are some other radio galaxies. You see here, this is shallower compared to Cygnus A. Cas A is shallower compared to Cygnus A. That means that in this region, you have a steeper power law of electrons for some reason. Similarly, here is another a supernova remnant. It also shows this power law with spectral index of minus 0.51. This is the slope here. Sometimes you you don't put this minus sign, but sometimes you do. So here they put a minus sign. So P minus 1. So minus P minus 1 by 2 is what. So this is equal to minus 0.5. So what is P? P is equal to 2. Right? Just from this, we can actually deduce that dn d gamma of these electrons, which are giving rise to this pretty shallow radio emission, is proportional to is proportional to gamma to the minus p. So you can, by modeling the synchrotron power spectrum, you can get something about the distribution of energies of synchrotron emitting electrons. This is very, very powerful. Okay, so so let me write. So in the next class, we'll actually go back to the more quantitative derivation of things, but this qualitative derivations and qualitative motivations will be good enough for a lot of purposes that you will have to deal with. So it's very important to have this qualitative understanding that, you know, the observed frequency is gamma squared nu cyclotron, and that power formula that, you know, synchrotron power is sigma T UBC times gamma square. So all these, just these simple scaling arguments, and the fact that the frequency dependence of power is only through omega by omega c will take you far deep into understanding things. You don't even have to like know very sophisticated and messy looking formulae that we'll talk about a little bit from the next class. Okay, then I'll stop sharing and